So I want to tell you about a discovery that we made about the fluid Earth system. And fluids referred to the atmosphere and the oceans. But we're really just at the start of this discovery. And there are many opportunities, I think, to push things further, and both in terms of understanding the Earth system, but also extending that understanding to other planets and perhaps planets around other stars. So I'd like to thank the Simons Foundation, which has provided some funding along with the NSF for some of the work that I'll tell you today. So the outline of this talk is going to be as follows. I'm first going to tell you the story of topology that first really entered physics through quantum physics. And a number of people here are exploring the ramifications of that. It's been going on for several decades now. And then we'll talk about some classical systems that which topology is playing a role. We'll see a movie of some of these. Then we'll turn to the fluid Earth system and talk about symmetries of the problem, symmetries of the fluid Earth system, and the shallow water equations, which are the simplest mathematical set of equations that exhibit the phenomena I'm going to tell you about, although actually we'll see that it was anticipated over 100 years ago. And that's going to bring me to the El Nino Southern Oscillation, the largest climate oscillation in the Earth system. And we'll look at some observations and try to interpret them from this new viewpoint of topology in the stratosphere. And think about other waves of topological origin, extensions of these ideas that we're only now beginning to work out. So back in the early 80s, and actually even before that, experimentalists noticed that if you take a semiconductor and you you connect leads to it, that's what these terminals are, to measure the conductance of electricity through it, and then you put it in a magnetic field, it surprisingly exhibits these sharp transitions in the resistivity or conductivity. This is known as the quantum Hall effect. And the magnitude of this resistance is related to fundamental constants, the charge of the electron and Planck's constant, which quantifies quantum mechanics. In fact, it's now the precision at which these plateaus occur is so great that this now functions as the international standard for resistance. And so this was a very surprising discovery, completely unanticipated. And there's a mechanistic way of trying to understand why, even in the presence of lots of dirt and disorder, which you can see in this picture, all the terminals with solder and so on, there might be this precision. This precision, even though we have this very messy system, in the presence of a magnetic field, electrons will spiral around in one particular direction. They'll form a cyclotron orbit. But at the edge of the material, that orbit can't complete. Instead, these semicircles happen. And so the electron is dragged in one particular direction, and it can't go back the other direction. That means that it's protected, to some extent at least, from the presence of impurities, things that might want to degrade the current, and perhaps gives us a mechanistic understanding of the quantization of the conductance. So as just shown here, where some dirt, some impurity is not able to deflect the electron as it would normally if there wasn't this unidirectional motion due to the magnetic field. But the proper mathematical understanding of this phenomena really came with a paper due to Thales and his collaborators, which was recognized in the Nobel Prize that was given in 2016 to David Thales, as well as two others, in which he related the conductance in the quantum Hall system to this quantity. this mathematical quantity involving wave functions, which at the time they didn't recognize is actually well known to mathematicians as the Chern number. And the important point is that this is an integer, and so it tells us that the conductivity is very precisely determined by the mathematics of topology. Now, I'm not going to go into further details here, but we're going to see how this plays out in the classical context of waves in the atmosphere. So let me remind you, if you've forgotten, or tell you if you haven't learned this, of what topology is. Topology is basically the qualitative shape of objects in a general sense. So this famous example here, we have a coffee mug which has one hole in it. And if it were made out of Play-Doh, it could be deformed into a donut without tearing the Play-Doh. And that donut has still one hole in it. If we wanted to get rid of that hole, we'd have to make a cut. So as long as we don't do something violent like that, then there's something that's the same between these two objects. Likewise, the Mobius strip, a strip of paper which is attached to itself, forming this loop, but with a twist, is topologically distinct from an untwisted piece of paper. We'd have to cut that piece of paper if we wanted to make it an ordinary loop. Then a little bit more closely related to what I'm going to tell you about, we have what's called the hairy-ball theorem. So if we had a sphere, a ball, which had little hairs on it, and we wanted to comb them flat, we would find that we couldn't do it. There would always be a cowlick or some sort of defect on this sphere. On the other hand, if the hairs were covering one of these donuts, we would be allowed to do that. So there's this qualitative distinction that is another manifestation or way of thinking about topology. And this is, in Europe, this is called the hedgehog theorem, because in Europe there are hedgehogs. And this work began when I was on sabbatical in Lyon, France. And I was living near Lyon, and I was raking leaves in the backyard, and I unearthed one of these creatures in hibernation. We had to figure out what to do, since they don't live in North America. I didn't know what to do. So I like to think that this hedgehog was trying to send me a signal about paying attention to topology, which at the time I was too dense to realize, but there it was. So Feynman, in his famous lectures on physics, in the chapter devoted to fluid dynamics, said, "The next great era of awakening of the human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot. Today we cannot see that the water flow equations contain such things as the Barber pole structure of turbulence that one sees between two rotating cylinders." This is called Couette flow. Today we cannot see whether Schrodinger's equation contains frogs, musical composers, or morality, or whether it does not. Now, I'm not going to attempt to address the second statement here, but we will see that topology does allow us some understanding of the qualitative content of some equations. And in particular, it can turn some complicated problems into simpler ones. So I mentioned quantum matter, and a more recent application of topology to quantum matter comes through a class of materials called topological insulators. This is the quantum Hall system with the currents flowing in opposite directions on the two edges that I told you about. But if we have spin, then we can have currents flowing in both directions of the spinning electrons spinning in different orientations. And these materials have been realized in various crystalline compounds. And the advantage of these materials over the quantum Hall effect is that we can do spectroscopy of them and see the excitation spectrum of these edge modes. In particular, plotting the energy versus the wave number, or basically the momentum, we can see that there are these well-defined particles, the electrons propagating in both directions. And we're going to see that there's an analog to this in the atmospheres that was actually done before, carried out before this experiment was done with quantum matter. So the important aspect of topology, it turns out, is not so much the quantumness. That's where it first found application, but it's rather the fact that quantum mechanics has a wave equation, the Schrödinger equation. So there's a wave-like nature, and it's the topology of those waves that's what is actually behind everything. So in fact, we can build classical systems of various types, where quantum mechanics doesn't play a role, but which have this same type of topological physics. And I'm going to focus on this one here, which comes from the lab of William Irvine in Chicago. What we're looking at is a collection of little gyroscopes, basically little toy gyroscopes, that are forming this lattice, and they're talking to each other through magnets. The magnets couple those gyroscopes together. And because all the gyroscopes are going to be spinning in the same direction, they have an influence similar to the magnetic field in the quantum Hall effect. So here's a little movie that they've made where they're going to jiggle one of these gyroscopes and see what happens. And the color is going to indicate where most of the motion is. And what we see is that it's confined to the outer edge of this collection of these gyroscopes. So this is one of these edge modes, similar to what I argued was present in the quantum Hall effect. And yet it's in a purely classical system. So this led us to ask the question, could some of these ideas be applied to the fluid Earth system? So why might they be applicable? For one thing, the Earth is rotating. And so here's a schematic of the rotating Earth. The North Pole is pointing up. We can notice some things about this rotation, some symmetries involved with this rotation. For one thing, if we looked at this rotating planet in a mirror, it would appear to be rotating in the opposite direction. So looking at something in a mirror, we call the parity operation, reverses the direction of the rotation. But also, we could reverse the sense of time. If we were to make a movie of this spinning sphere, we could run the movie backwards, and it would appear to be rotating backwards. And that is expressed through this famous theorem, CPT, the CPT theorem that physicists love. Here, C stands for charge, which we don't need to worry about, because here we're thinking about a neutral fluid. P is parity or reflection, and T is time reversal. Then what this says is that the combined operation of parity and time reversal leaves the system invariant. So if we were to look at this in a mirror, we reverse the rotation, but then if we were to run the movie backwards, the rotation would be restored. So separately, we say that time reversal symmetry and parity are broken by the rotation of this planet. And this is expressed mathematically in terms of something called the Coriolis force here, which says that when something is moving with a velocity v, then there's some additional acceleration that it experiences when it's on a rotating planet. And the important point here is that the vertical component of this rotation rate, the local vertical component, so here in New York City, we look straight up and we look at the dot product between that and this rotation, that this quantity here, which is called F, changes sign as we go across the equator. The Coriolis parameter changes sign, so high pressure regions on Earth in the atmosphere rotate in a clockwise direction to the northern hemisphere, but they rotate in a counterclockwise direction in the southern hemisphere. And that means that the equator is a very special place. It's the boundary between these two regions, each of which break time reversal symmetry in an opposite sense. So this is where we found that there are waves of a topological origin analogous to those in the quantum Hall system. But before we did that, we faced a number of objections and skepticism that this could actually work. There was this idea that, well, fluids are very simple, maybe too simple compared to quantum systems to support these types of waves. But that was easily dispensed with because we know that actually fluids are quite rich and we can have different degrees of freedom, velocity, heights, and so on. So I wasn't too worried about that. Perhaps a more serious objection is that this is a continuous fluid. There's no lattice. And all the other examples involve lattices, lattices of atoms, lattices of our gyroscopes. Perhaps the lattice is essential, but that turned out not to be the case. And then, would it be true that topology would still allow us to make predictions about the waves that are traveling in the system? That's called the bulk interface correspondence, the idea that the topology away from the interface, in this case the equator, says something about the nature of the waves at the interface. So let's take a look at the fluid Earth system. Here we're looking at it in an infrared wavelength from a satellite view that is focusing on water vapor. And struck by a number of things. First of all, you can't see the continents because the water vapor is so opaque to these infrared photons that we're just seeing the upper parts of the troposphere. Secondly, the equatorial region differs dramatically from the regions at high and low, at high northern or southern latitudes. We see this kind of pulsing, which is due to the buildup of clouds during the daytime in the tropics, and then fading away at the nighttime. Whereas up at the high latitudes, there are these beautiful wave-like structures that are traversing. And at first, I thought these high latitudes were the region to focus on because of those wave patterns. This seems a little bit less promising. It's much more turbulent and chaotic. But after many failed attempts, we realized that actually the equatorial region was where we should be paying our attention. Now, if I had been paying closer attention, not just to hedgehogs, but to classic textbooks about geophysical fluid dynamics, I would have opened, for instance, this one. And if I had done that, I would have found this plot in it, which when I show this to any quantum matter physicist, they immediately recognize that this is the signature of a topological wave. And yet this has been sitting around inside classical textbooks for 100 years. And no one had made this connection. So I think it actually speaks to the barriers between the different areas of science, that there's this lack of communication. Geophysical fluid dynamicists don't talk to quantum physicists and vice versa. And, but there are connections waiting to be made. And I think the Simons Foundation actually is a place that can encourage these kinds of interdisciplinary connections. So we're going to return back to this shortly. Here's an experiment that's done with some fluids in the lab. What we're seeing is we're looking down on a wave tank, and it has water with a layer of oil on top of it. And so, as it's stimulated, as there's height fluctuations in this fluid, then we can see the waves as an interference pattern. So it just helps with visualizing these waves. Now this tank isn't rotating, but if I put the tank into rotation and the camera is rotating with the tank, now we see that there's this continuous wave circulating in one direction, unidirectionally, and it's bound to the origin, much like we saw with the gyroscopes. So here's a continuous fluid system that exhibits the Kelvin wave, what's known as the boundary Kelvin wave, which we now know has a topological origin. But for some technical reasons, this is actually a little bit more complicated for us to apply our topological ideas than the fluid Earth system, the whole planet. Just to show you Kelvin's paper from 1879, it's very readable, on gravitational oscillations of rotating water by Sir William Thomson. Here's the first equation that shows one of these topologically bound modes, this coastal Kelvin wave, exponentially trapped at the coast and having a linear dispersion relation. So I believe that this is the first place where topology entered into physics, although Kelvin himself didn't realize this connection. He simply directly solved the wave equation. So let's start to look at this rotating planet in more detail. And what we're going to do is look at a very simple model for either the ocean or the atmospheres, where we have a denser fluid underneath a lighter fluid. And what this allows for is for gravity to be a restoring force, the buoyancy of the fluid to be the thing that will allow waves to propagate. And so in a computer simulation, if I were to drop a rock on such a spherical planet, the waves would propagate out and go to the antipode, and then they just would bounce back and forth, back and forth. And we can see that on this cylindrical projection. The waves, they look like they're bouncing, but what they're really doing is they're just passing through each other, going back and forth, back and forth. And actually, as we'll see in a moment, Earth itself provided a nice example of this just a few years ago. Now, as it stands, rotation hasn't been turned on. This is a non-rotating planet. So let me repeat the same experiment, but allow for the restoring force of the Coriolis force due to the rotation. And what that's going to do is it's going to affect motions in the horizontal direction. And now the character of that wave is completely different. Instead of spreading out in all directions, it's confined to the equator. This is the equatorial Kelvin wave moving along as this pulse, and it'll just go around and around as time goes on. There's actually a second wave that is antisymmetric with respect to the equator. It's called the Nino wave. You can see that the colors, like we have orange on the top and then green below, or vice versa. And it's dispersive. Its phase and group velocities are different, so it has this kind of phasing appearance, unlike this pulse, this Kelvin wave pulse. And both of these waves have been seen in the atmosphere. So I mentioned that the Earth provided a nice illustration of this physics. This is a short movie of the eruption of the Hunga Tonga volcano in the middle of the Pacific. And what you can see is a pulse. You can see a pulse, a pressure wave going out at the speed of sound. And that pressure wave went all the way around the world and came back, and it went around. It was observed going around several times, much like the simulation we saw before. Here, this is a pressure wave instead of what we call a gravity wave, where the force of gravity was important in our simulations. This is just a compression of the atmosphere, so the Coriolis force didn't affect it. So let's turn to some observations of the Earth. This is looking at the sea surface height of the Pacific Ocean as measured by a satellite bouncing microwaves off the surface of the ocean. So a radar, essentially. And the color indicates whether the water is higher than average, the red color, or lower than average, the green color. And the amplitude here is only plus or minus about 20 centimeters. So rather small variations. And we're going to look at this over a period of a few months between 2009 and 2010, so during the winter. And again, we have this change in the Coriolis parameter. So as I mentioned, the high pressure zones rotate in opposite directions on the two sides of the equator. And there's this pulse of warm water that moves across the Pacific. This is characteristic of the El Nino. When there's a warm pool of water off of the coast of South America, it has global impacts on the climate. And for instance, there's a greater probability of heavy rains in the southwest of the United States during this phase. Right now, we're moving into the opposite phase, the La Nina phase, where the warm water is over on this side of the ocean, but that will reverse every few years. And this is the Kelvin wave here in the case internal to the ocean. So this is a Kelvin wave in the water. And the coloration indicates warmth. It's not just height, but that's equivalent to warmth because warm water expands, and that leads to above average heights. Here's a three-dimensional view of that wave. And so this is a cross-section across the equator, and you can see that it's an internal wave. It's internal to the ocean, below the surface, and is this propagating from the west to the east. So it has this unidirectional character to it. And then eventually it ends, and we have this backflow of waves, a different type of wave going the other direction. So now I want to turn to some of the mathematics of this wave. And so we'll use the shallow water equations, which are closely related to the equations that we simulated in the earlier simulations. So the wave, we can just think of this as, say, water and maybe air up above, or perhaps even a vacuum. We'll neglect the density up here. And this water has some height or some depth, and it extends in the two horizontal directions. So there are two equations that govern the flow of that water. They're basically manifestations of conservation laws. The first one is simply the conservation of mass. It says that if the water is pushing out, maybe due to gravity, then the height must drop. So that's the conservation of the water mass. And the second equation is Newton's law, equation F equals ma, that says that the acceleration has a contribution due to gravity and a contribution due to the Coriolis force. So there are these two forces acting on the fluid motion. And now we're going to do a little bit of mathematics. So first of all, I'm going to drop this nonlinear term, and I'm going to replace little h by the average height. That's just to simplify the equations to make them linear. And once they're linear, then I can do a normal mode analysis. I can find the frequency of the waves as a function of their wave number, or so as a function of their wave number in the x and y directions, kx and ky. All I have to do is diagonalize this 3 by 3 matrix. And if I do that, I can find the frequencies. There's one wave that has absolutely zero frequency. That's due to the balance between the Coriolis force and the pressure. And then there's two waves that have positive and negative frequency. If we plot those out, then the spectrum looks something like this, with this positive frequency waves, and then here's this green is the zero frequency wave. So for those who have been working with topological physics will immediately suspect that there may be some interesting topology behind this, just based on that dispersion. And it becomes particularly clear if we look at the wave functions themselves, where there is a singularity in the wave function phase as we approach the origin in wave vector space. So as that singularity is the signal that there's something interesting going on with topology. So we call this phase diagram, let me actually go through this first. So if we look at the South Pole, then the dispersion relation looks like this. And if we go around the 0 point in wave vector space and plot the phase of the complex amplitude that defines the wave function, then we see that there is an anti-vortex. These arrows, which indicate the argument of this complex amplitude, are reversing direction as we go around. They go through minus 2 pi radians as we're circulating around 2 pi radians. If we repeat that in the North Pole, then we also have a singularity, but it has a positive relation. It has a winding number of 1 instead of a winding number of -1. So if I'm paying attention to the positive frequencies, I've colored the positive frequency modes here red and blue over here, blue for negative, for winding number of -1, red for winding number of +1. And that means that at the equator, there is a transition. There's a topological transition characterized by this thing that we call a Weyl singularity, where this gap vanishes. That's where the Coriolis parameter is 0. And we don't have any defined topology. We can only define the topology when these bands are separated in this way. And because the winding number changes by 2, that tells us that at the boundary between these two phases, at the equator, there need to be 2 waves, the Kelvin wave and the Unai wave. And so those are the waves that are predicted by this topological argument. All we had to do is diagonalize a 3×3 matrix in order to understand this physics. We didn't have to solve a partial differential equation. So the existence of these equatorial waves was realized by geophysical fluid dynamicists back in the 1960s, where they worked out this phase diagram by directly solving the wave equation, which is technically quite a bit more difficult than what we just did, but not that hard. And when we submitted our paper for review, we had this referee response. The question of why the equator supports a unidirectional wave, the Kelvin wave, is interesting scientifically and important mathematically. I've asked the question myself and been unsatisfied with my own answer, as well as that of other geophysical scientists. So there was a realization that there was something suspicious about these 2 waves. There's something that they didn't really understand. They could see that they emerge from a direct solution of the fluid equations of motion, but why there were just these 2 waves was rather mysterious. And now topology provides the answer. So we can actually observe these waves similarly to what was been done in quantum matter, because clouds move around, shift around in the Pacific, tracking this warm pool of water. And we saw that this warm pool of water moves across the Pacific with the Kelvin wave. So if we look at the spatial location of clouds from satellites over time, then the spectrum of the waves can be backed out. And here they are. So this is the Kelvin wave as a function of wave number and frequency. We see this linearly dispersive wave. And here is the Unai wave, this thing that is dispersive. So this was done prior to the experiments on topological insulators. And we asked the question, well, can we get more directly at the topological nature of the waves in the system? So we asked ourselves, can we calculate the winding number directly from observations? Which I will come to in just a moment. Actually, I want to tell you a little bit more about the El Nino first. So as I mentioned, the El Nino has these far-reaching effects on the climate. This warmer sea surface temperature off of South America has these so-called teleconnections throughout the globe. And you can actually see the effects of the El Nino in the rising carbon dioxide in the Earth's atmosphere. You'll notice that it's not completely steady. And these little events here where it suddenly jumps up, we discovered are associated with the El Nino. This is some work that I did back when I was a graduate student. There was a strong correlation we found between temperature and carbon dioxide. And we now know that the El Nino tends to release carbon from the various reservoirs on Earth, such as forests. During El Ninos, forest fires in the tropics are more common. Now, there are other oscillations of the climate system, and this is perhaps the most spectacular one. This involves reversals of winds in the stratosphere up, say, 20 kilometers altitude. over a periods of about every 26 to 28 months. So it's called the quasi-biennial oscillation. What's plotted here as a function of height and time is the velocity of the winds in the east-west direction. It's kind of an amazing oscillation because almost nothing in the climate system is so regular as this oscillation. In fact, nothing is this regular. So these waves are believed to be driven by Kelvin and possibly Yanai waves emanating from below, excited from thunderstorms down in the troposphere at lower altitudes. So we thought this would be a good candidate for us to try to calculate the winding number. And just to emphasize, we have this non-trivial winding number at the frequency of these Poincare gravity waves, here the anti-vortex, here the vortex. But if we go down to low frequency waves, these are the waves that were that flat dispersion we saw earlier, then we have what's basically a domain wall, has trivial topology. So we looked at actual observational data taken around the world up in the northern hemisphere and constructed this winding number, and we found that at the high frequencies, more than one cycle per day, that there is this vortex as expected in the atmospheric observations. So when analyzed this way. So here's a first direct signature of topology in Earth's atmosphere in this case. At lower altitudes, down here where we live, then there's a lot of turbulence and this pattern is destroyed and we don't have these waves at low altitudes. We've also been working this out in position space instead of just wave number space, which I showed you before. And we think that this will be a nice tool for looking at sparse data sets where we have irregularly spaced observations. So there are many other types of waves in the Earth system, and I want to focus on this one, the Madden-Julian oscillation. This is a pattern that also is found along the equator, a pattern of rain that moves slowly across from west to east, and leads us to the question of whether there might be a topological explanation for this oscillation. This is one of the big problems that remains unsolved in climate physics. Recently, the Simons Foundation awarded a Pivot Fellowship to Alan Dorsey, and I'm going to be his mentor. And Alan will be looking at exactly this problem, trying to understand whether the Madden-Julian oscillation shares these topological physics that we saw for the other waves. Kelvin waves may have been seen in the atmosphere of Jupiter. So here we see a view from New Horizons, that's the spacecraft that went past Jupiter on its way to Pluto, and from even old Voyager 2, which are focused on the equator, and you see this kind of structure, which may be an equatorial Kelvin wave. So one could imagine repeating the experiment or the experimental analysis I showed you for the stratosphere of Earth on Jupiter from better observations to see if there's a topological signature of these waves. Many of the planets in the solar system, especially the ones that are slowly rotating like Venus and Titan, which is really a moon, but we can think of it as a planet that has a very thick atmosphere, exhibit something called superrotation, where the winds in the equatorial region are rotating in the same direction as the planet. That's different than Earth, where the trade winds are blowing the opposite direction of the Earth's rotation. So we call that superrotation, and that also occurs on Jupiter and may occur on exoplanets. And Kelvin waves have been implicated in driving superrotation on planets. And the story is still incomplete, but this may be another place where our topological tools could help clarify the origin of this phenomena. Mathematically, one way to think about this is through the interactions of waves with mean flow. So the mean flow would be the circulation of the air in the planet, driving this super rotation. And there's a kind of decomposition of fluid waves and mean flows, this solid line here, in terms of Feynman diagrams. It's called the quasi-linear approximation. It's a kind of mean field theory that's rather similar to Hartree-Fock theory, for those who know about that. And this may offer us a way in to thinking about how to use these topological ideas in the context of nonlinear wave systems. So quantum mechanics is completely linear. This issue doesn't arise, but in fluid systems, we are dealing with nonlinearities. I dropped those in our simple analysis, but if we have large amplitude waves, nonlinearities are going to be important. And we need to learn how to deal with topology in this context. And we're beginning to do some work on this, but this is still at the very early stages. Waves of a similar origin should exist in gaseous plasmas. So we've been doing some experiments at the Large Plasma device at UCLA. This is basically a solenoid. Here you can see the coils that are producing an axial magnetic field in a cylinder that is something like 100 feet long. And when we solve the equations of electromagnetic waves in this plasma, we predict the existence of edge modes very much like the Kelvin boundary modes that I've been discussing. So we've been doing an experiment. It's quite difficult, especially for a theorist like me, to go into a lab and learn how to do these things. This is our leader here, Zoe Zhu, who a number of you know is a postdoc at Stanford, so she's leading our effort. And this is Troy Carter, who until recently was the director of the Basic Plasma Science Facility at UCLA. So we're going to be going back in February to do some more experiments. This is just showing our theoretical prediction for one of these unidirectional waves in a plasma. Other scientists have been looking for waves of topological origin in stellar atmospheres and also perhaps in the interior of stars. And so there's a region in the center of the Earth called the tachocline that separates the convective zone from the radiative zone in the center of the sun, and there's a strong magnetic field. Over here, at this separation between those two zones, something called the stratification parameter basically goes to 0, and so there may be a topological phase transition there, which might be discernible in astroseismology, looking at waves, looking at the oscillations of the surfaces of stars. So I'd like to end with this question: what new waves of topological origin are waiting to be discovered? Thank you.
For a terrific talk. We all of us who knew Jim Simons very much miss him. And Jim was a regular at these lectures. And I know this is a lecture that he really would have enjoyed, seeing the deep connection between topology and fluid dynamics in such a wide range of systems. So I'm going to take my privilege as the host and start with a question. And with the plasma systems you're looking at, these are look like tokamaks? Or would you expect to see sort of twisting structures and stellarators around the edges?
Possibly, yeah. So we're looking at a particularly simple geometry just because it's easier for us to analyze experiments. But in the back of our mind, we're thinking about the edges of plasmas and tokamaks. Possibly these waves could be important for transport of heat And maybe they could be used also to probe the interior of the plasma using that topological protection. This is still very much in the early stages, though.
Questions? In the back?
Let's see.
In the context of nonlinearity.
Yeah.
More about that.
Well, I can't say too much. We've done some numerical experiments. Maybe I'll just show you one where we turn up the wave amplitude in those shallow water equations. And let me see if I can, just to see what happens. And right, here we go. So in this first simulation, what you're seeing is that equatorial wave moving along. But what you don't see here is that over on the left side, I've decreased the depth of the water so that the wave slows down. And that means that its amplitude is going to increase, just like a wave approaching the coast of the ocean, from the ocean. Here it emerges unscathed. But if I turn up the amplitude of the waves further, and let me just advance this, we see it propagating. And now, as it enters this region, it gets so large that the wave starts to break. And so, although the energy continues to propagate in the same direction, it's highly distorted there. And finally, in this third simulation, the wave amplitude is so large that even before it gets to that shoaling region, it starts to break and distort. So how we understand this, though, right now, nobody really knows, I think, how to combine the topological ideas with nonlinearity. One thing that might be interesting to investigate is whether a soliton can be formed by taking perhaps that dispersive Yanai wave and tuning the nonlinearity so that the dispersion is fighting against the nonlinearity. So that might be an interesting mathematical exercise and perhaps would yield some insight.
So two questions. The first one, which I'm not quite sure I understood, is how does dimensionality play in here? Because when you showed this picture of the atmosphere, I mean, to my understanding, there are regions of the Earth where there is significant vertical movement in the air and regions where there are not. So when there are not, you have essentially two-dimensional flow. And there you have the square of the vorticity is conserved and you have an inverse cascade, and this gives these large vortices. Now, if you have, in 3 dimensions, these topological ideas still apply. And then the second question is maybe related to this last. I mean, there is this KdV equation, various integrable equations which sort of balance
Yes.
and produce soltons. And so you would expect some topological ideas to apply there?
Oh, well, let me just address the second question first. I'm not suggesting topology be applied directly to KdV, although perhaps it could be, but instead that there might be an effective KdV equation for this two-dimensional system because of this reduction to a one-dimensional motion. And so that is the direction I'm suggesting there. Regarding your first question, yes, I mean, the atmosphere is turbulent, or at least there's turbulent parts, especially down at lower altitudes, the boundary layer. But actually, as you get up higher, it tends to be more laminar. Nevertheless, there is some nonlinearity. In the waves that we've been looking at, the gravity waves, their amplitude is relatively small, and it's up in the stratosphere where the turbulence is relatively low. So that's a particularly easy region to start to look for topology. As we go down into the troposphere, all of these effects that you're mentioning become important, and that's where we need a better understanding.
Does genus play any role in any of this?
Yeah, well, of course, there aren't any planets that are shaped like donuts as far as we know. But it would be very interesting if one existed. So in some of the some of the imaginary planets we have a planet with 2 equators. That allows us to flatten out the planet and make it a donut, essentially. So for mathematical convenience, donut planets are much nicer than spheres. But yes, there is this connection, and basically the number of equators of the planet is connected with the number of waves. Yeah.
Are there any wave phenomenon that are protected by these topological things, so they cannot dissipate?
Yeah.
So they're preserved and kept going forever. Is there
Right.
something?
Well, we see an example of that here in this top simulation I showed you. That wave passed through this dirt, this perturbation, and yet it remained unscathed because it had this unidirectional character. So there is a kind of topological protection for the same reasons that there are in, say, topological insulators.
We have time for one more question. Yeah.
So basically, my question is regarding from the idea you mentioned that on the upper level atmosphere, most of the waves or perturbations is basically horizontal rather than the vertical. You mentioned the turbulence in the vertical direction is more on the lower level, but many of the concerns regarding, for example, the polar vortex stuff is saying like they monitor the upper level polar vortex.
Yes.
And then the perturbations can propagate down to the surface.
Yes.
So from the topology perspective, is there any indications to tell how or what kind of perturbations in the upper level can be propagated down to the surface level?
Yeah. These are good questions. What I can say is that we can repeat this topological analysis in a continuously stratified fluid, and it works, but now we can think of it as a collection of topological insulators, essentially. But how, in terms of interactions, which is what you're really getting at, again, we're just beginning to think about that. And so I'm hoping maybe some people here can contribute to better understanding that. That's going to be a big problem, but very interesting one.